Perfect. Okay, so let me start here. This is meant to be a bit of a general talk, but don't be fooled. There is a lot here, a lot of science in this talk. And every topic I will discuss, and because I'm trying to keep it to a half hour and then give you a walking tour, I've cut it down a little bit to only 5 things, but I'm trying to give you some of the more exciting things that are going on. And as I discuss it, and perhaps at the end, feel free to ask questions if you have any. And then, as I'm walking around, it would not be difficult for me to talk more about any questions or answers that you may want to hear. But again, every one of the topics can be, one could give an entire talk, frankly, on any one of the 5 topics. So I'm going to go, start now. And if there are questions, again, go ahead and save them or give them to me at the end as I walk and talk. All right. So you might be aware of this fact, although it's very interesting and an area of some research, that the oldest glasses on Earth were not made by human beings. They were not, mankind didn't start working with glass until relatively recently, actually. But glass itself as a material has existed much, much, longer period of time than anything human beings have ever done. So in here, for example, I can show you, this is a glass inside meteorites. And so you'll see right here, this little tiny sort of glass particles inside the meteorites. These are 4 billion years old, which is roughly the same age as the beginning of our solar system. So we can actually find glass that was made by nature that is at least 4 billion years old. Again, a lot of this depends on the particular age of the meteorite. I would not be surprised if one could find even older glass. So obviously it's a material that can be very ancient. I also want you to remember that this is 4 billion years old because there is one of those urban legends that states that glass is a liquid, a very viscous liquid, and that therefore over a period of centuries, glass windows will actually flow downwards and settle at the bottom. That is completely false. And one way you would know that, obviously, is that if that was true, then glass particles that are 4 billion years old, anything on the outside would have obviously spread out over time. That does not happen. Glass is like any other material, like any other metal, like any other ceramic, like any other alloy, and it is a solid. Okay, it does have some peculiarities, which I'll get to at the end of the talk, but it is a solid. So this one is extraterrestrial glass coming from meteorite that have, reached Earth, of course. But you can also find glass beads on the surface of the moon perhaps from meteorite impacts there too, perhaps from long dead volcanic activity, from the formation of the moon, which again, some speculation, it came from an impact of something with Earth. But in general, this is what they look like. So you can actually find pretty glass, beautiful glass on the moon. And that's a very, again, interesting sort of a idea to think about, that you can actually find, once again, glass in the most remote corners. And again, very old in terms of its presence in the universe. These are not big, for the record. They are small. They have been studied. I have a colleague who unfortunately has passed away, who remembers receiving some of the early glass from the moon or early rocks from the moon to study and look for glass. And it was brought by a military escort with people carrying the briefcase with the solar rocks attached to their wrist. It was a very secure environment right during the Apollo missions, but it is very interesting. And of course, people have found glass in the moon. So let me move on just for the sake of time. Here is some more materials that you can find here on Earth. Again, glass, not maybe as old, but every time lightning strikes, as it does here, for example, and it gets excavated, Lightning can fuse sand, in particular silica sand, and it can create beautiful patterns, glass patterns that can then be excavated from the beach, from the sandy area. You can also find obsidian, which is this rock over here, dark typically. You may have seen some of that perhaps in your department. Obsidian is a volcanic glass, volcanic glass, and it's a very useful material. Many of you perhaps know that some early civilizations used it for arrowheads. To this day, we can find Native American arrowheads here in the United States that have been made out of obsidian. And so you can find also in Central America and in other places. So very useful material right from the beginning. Knives, arrowheads, and others were made from obsidian. Libyan desert glass, on the other hand, was a mystery. It's not in Libya. Let's begin there. I apologize. I don't know why it keeps moving forward. It's a mysterious material because it was found in a desert with nothing surrounding it. And yet, as you can see, it is a rather beautiful and sometimes pretty large piece of glass. And it was a bit of a mystery. It was not clear what had caused it. The latest theory, I believe, if memory serves, is that it was a volcanic byproduct of a long dead volcano. But for many years, it was a mystery, and it has been collected and studied. But it is, again, a very interesting topic. Every now and then in the world, you find these pieces of glass that have no obvious origin. Okay, so this is natural glass. And it's very interesting because, again, human beings, for the most part, have no role in making this glass. But it is a topic of great interest to geologists. It is a topic of great interest in some cases to glass scientists. Give you one last reason for that. In the United States and as well as in France and other places, one of the ways that nuclear waste is being disposed of, meaning that after nuclear material has run its course in a reactor, it remains radioactive, it remains dangerous. And the one thing you probably don't want is for that radioactive material to end up in the water supply, for example. So after many years of discussion, the preferred solution is to grab the radioactive material, mix it with some other chemicals, take it to a high temperature, and turn it into a glass. And this is being stored in the United States in very large containers, about maybe 5 meters tall by at least a meter or so, maybe 1.5 meters diameter. And inside this container, it is glass. It is fused glass that in turn, embedded in it, has a radioactive material. But one of the requirements for this process of nuclear waste immobilization is that the material has to last a long time. It has to be very durable. And so people have actually used natural glasses like this to see if under the right conditions, for example, after periods of rain, after periods of drought, after periods of, cyclic weather events, how well has the glass endured? So some of these materials have been used to generate models, okay, computational models typically, to predict how durable and how long lasting these special glasses for radioactive waste disposal will survive. So even these have other practical technological applications. Okay. As you guys probably have studied or have learned a little bit, glass is actually quite strong. The theoretical strength of glass is very high, actually. It comes always as a bit of a surprise when people do the calculations that that glass itself should be an extremely strong material. Unfortunately, in our daily experience, glass is not such a durable material. We have all dropped a bottle or we have dropped a cell phone and discovered that glass in many cases can be quite fragile. It can break, it can shatter, it's brittle. But interesting enough, the reason why that happens is actually very interesting. It is because ultimately glass can simply not be made under normal conditions without creating flaws on the surface. it is essentially impossible to create a surface perfect glass. It's a topic of great study, believe me. There are literally certainly tens of millions of dollars being spent every year in research for developing stronger glasses. The cell phones that you guys have been the main glass, which is the top glass. There's actually 4 layers of glass on an average cell phone, iPhone or Samsung or whatever. So you have 4 layers of glass, but the one that we normally don't care the most about is the top one. And that top one is, depending on whose brand you buy, it's either made by Corning in the United States or Asahi Glass, Dragon Glass, or some other similar providers. Those glasses have been strengthened through a completely different process. Very interesting process. We'll get a little bit into it here in a minute. But those glasses, even those glasses are, number one, they are not completely break resistant. And number two, and even maybe more surprising, the glasses you have in your hand now are about, I think, approximately the 10th or 12th generation. So people have already come up with 12 different improvements on those glasses, always in a competition to make them better and more durable. And they have gotten more durable, as well as other properties that the manufacturers like nowadays, they're also antibacterial, for example. In any case, the point is that those are an interesting example of something you can achieve slowly as you improve the strength of glass. The problem, again, is the flaws. The flaws on a surface of a glass concentrate stress. And therefore, whenever you have a problem, like dropping the glass, anywhere you have a flaw, you have a point at which a crack can start. And that's a very bad thing, because a crack can start on the glass, and even if it's small, it will propagate over time. Obviously, in many cases, it propagates instantaneously when you drop it. And if the glass, of course, if the crack goes across the entire length of the glass, then you no longer have one piece, but 2. Again, many of you have dropped pieces of glass in your life. You know what I'm talking about. It can shatter in many pieces. And again, there is a lot of research in how to prevent this from happening. The solution, it turns out, has not been to get rid of the flaws. You would think that would be the obvious, get rid of the flaws, but that's very difficult to do. So what we instead do is try to prevent the flaws from having cracks that grow. And so, as you guys probably have studied in class, tempered glass. Tempered glass was originally done with temperature, and it can actually essentially put the top layer of the glass into a state of compression. And literally, the glass is trying to push against itself. So if you ever start a crack, the crack will heal itself. It will shut, it will close before it has a chance to spread throughout the glass. That comes with some penalties, which we won't get into, meaning that if you ever go beyond the surface, the glass will shatter catastrophically. But let's set that aside for a moment. The problem with your cell phone is that the glass is too thin to do thermal tempering. And so instead, what normally we do with this type of glass is that we do an ionic exchange. We remove sodium, for example, and replace it with potassium. The ionic radius of potassium is larger, which means that once again, that top layer of glass gets purposefully placed in a condition of compression. And that condition of compression, of course, does the same thing. The advantage being that you can have a glass which is 40 microns thick. So that's about less than half of a human hair, and still have it tempered, still have it compressed. So that is an amazing technical achievement, even though it was developed in the 70s. It is now the bread and butter for solving the issue of strengthening thin pieces of glass in cell phones, laptop displays, etc. So that's kind of a cool use of it. Just for the sake of time, I'm not going to show you the video. This is a picture of what happens to tempered glass when it breaks. It is catastrophic, although that is not as bad as you may think. if you have ever broken a bottle, you know that it is somewhat dangerous to pick up the pieces. You can get cut. But tempered glass tends to break into very small fragments that are roughly hexagonal in shape. Not really. I mean, there's a variety of shapes, but they are not very sharp. And so if a tempered glass shatters, it's unlikely that you will receive deep cuts, maybe some skin cuts, but you are unlikely to get cut deeply. And so tempered glass is therefore also used in windshields, car windshields, which in turn it's called safety glass. They have a piece of polymer in there to prevent the pieces from flying around. But in general, though, it's a clever design to try to prevent it. Again, I have this video, if I can go back a second. I have this video that is very interesting. Gopi, you're recording this. I'm happy to send you this presentation, and then the students can look up the video in their own time, just for for keeping the talk brief. Whoop. So there is a wonderful video filmed at 100,000 frames per second of a tempered glass shattering. And you can literally see the shock wave, which you cannot see here, propagate and explode, okay? So the next topic I want to talk about, number 3 here, again, in this tour de force of a half hour, is that you can do some wonderful things, believe it or not. And now we're getting into more cutting edge technology. Tempered glass, you may have known about. I'm not surprised if you, or maybe when you were a young person, learned about it in school, or maybe from a relative or something. That's normal. But some of what's happening nowadays, some of the research and the work and the products that are being developed nowadays, which refers to glass in the human body, are extremely useful. They're cutting edge, and there is a lot of research going into this right now. So if you go back to the Middle Ages, to the age of the Renaissance, people used to believe that you could eat ground glass to prevent people from poisoning you with glass. These are, again, legends of the time. The truth is that people have had a logical fear of having glass in their body. Why would you put glass in your body? It seems like a completely crazy idea. Glass seems dangerous. It seems like it can cut you. Why would you ever use it inside your body? Well, it turns out that you can use it inside your body in a large number of ways. It started around 1971. A gentleman called Larry Hench developed the first, quote unquote, bioglass. Bioglass is extremely useful. It has been used for most practically for bone reconstruction. So the composition of the bioglass, the bioglass that in particular, the first bioglass that he developed, does well in the human body because it can actually result in the formation of hydroxyapatite, which is one of the bone components. And so you can place it in a broken bone, if you would, and it will aid in the growth and restoration of the regrowth of the bone after a fracture, for example. That's great. There are some flaws in it. You cannot use it for bones that are load-bearing. For example, your tibia, femurs, things like that. You cannot use it. You have to use it for bones where there is not so much. If the chance that the bone will snap this way, that's too dangerous. You can't put it there. But even that has been solved recently with the use of multiple strands of glass, creating a bundle, which is much stronger. So people have been doing that type of glass since the 70s. Another type of glass in the human body that has been very practical and very useful is let me go back to the talk here. There we go. Is the use of glass microspheres. These are designed for cancer treatment, in particular liver cancer treatment. The way it works is that you create these microspheres. They are typically borate glass, so it's boron containing glass. It also typically contains perhaps a rare earth element in it. And the rare earth element is subject to some bombardment in a radioactive sort of setting, some kind of reactor, if you would, and that turns that element into a short-lived radioactive isotope. So a radioisotope, typically something like cesium-137. There are others, americium, there is others that are that way. but they are short-lived. So they typically have a half-life of about 60 hours. What that means is after, I don't know, 300 hours, about 5 half-lives, there is very little radioactivity left in that material. So what you do then is that, again, you have these microspheres, you have the rare earth material in there, you turn them into these radioisotopes, active but short-lived, and you place them inside the human body. In more specifically, you put them in a vein, something like an artery, something like the hepatic artery, in which the microspheres are going to be delivered. They are small enough that they can travel down the artery until they reach the liver. When they reach the liver is very much, as you probably learned from school, right? It's a filter for your blood. And so that filter will trap or stop these microspheres. That will have 2 beneficial effects. Number one is the place where these spheres stop is typically the place with the most irrigation of the liver, and that typically is where the tumors are. The tumor, one of the things about tumors, they tend to grow many connections. They're growing very rapidly, so they need a lot of blood infusion. So many of the spheres will end up at the tumor, at the site of the tumor. Those spheres will then do these 2 positive things. Number one, they're going to deliver a heavy dose of radiation very much right next to the tumor, which obviously makes it good as a radioactive treatment. But the second thing they do is that they tend to block the delivery of blood to the tumor, at least for some time. Simultaneously, these glass microspheres are, of course, dissolving. And the reason you want them to dissolve is because you don't necessarily want them permanently in the human body. The radioactive material, after about 300 hours, no longer does anything. And you want to get rid of it. And so the microspheres will dissolve over a similar period of time. And therefore, after about, let's say, a week, or I guess it's more than that, maybe on the order of about maybe a couple of weeks, actually, they are completely dissolved and they are expelled by the body together with the remnants of that radioisotope that is no longer quite so active in there. So this was designed through a very specific composition of boron glass or borate-based glass, okay? All right. Teeth, it's another area where there has been a lot of work recently. There is now at least one toothpaste in the market that utilizes a similar idea, glass, which will then continue to deliver fluorine or fluoride, to be exact. Most of the time, every time you buy toothpaste, it says it contains fluoride. That's great, except that within about a half hour of you brushing your teeth, your saliva has rinsed your mouth and you no longer have much fluoride left. This toothpaste contains particulates of glass with fluoride that get trapped. They are small enough that they get trapped in some of the holes in the dentin. And when they get trapped in here, they can release the fluoride, go back, over a period of many hours. And so this is much better for your teeth than just having toothpaste, plain toothpaste, if you would. So very interesting. The toothpaste is available in Europe. And as we just saw, sneak peek, is now actually in the United States. It's finally approved in the United States. So there is glass containing toothpaste or bioactive glass containing toothpaste in the US. You can also do other things with glass. Last week at the National Day of Glass, there was a wonderful new talk on this topic. Tooth replacement teeth can be made with glass ceramics. And now there is actually an effort to make very specific glasses that can be hardened very quickly. So shaped, molded, and then hardened very quickly. That is an area of research right now. And what people want, I'm not sure exactly how many of you, you're fairly young students. Hopefully not many of you have gone to the dentist yet. But when you go to the dentist, they typically take a mold of the teeth that they're gonna perhaps replace. That mold gets sent to a separate company. The separate company manufactures these teeth. Takes about 2 weeks. They get back to the dentist. You have to go in for a second visit, and they replace your presumably teeth that have decayed with these new glass teeth, actually, or glass ceramic teeth. They're trying to do that in one visit. You go there, they take the mold, and they, in the same office of the dentist, they can actually manufacture your replacement teeth. So they're trying to attain that. There's also ideas of 3D printing, but still, this is what they are trying to do right now. A glass ceramic is a glass that contains a controlled amount of crystal in it. And once again, that can also prevent cracks from propagating. So it's a different mechanism for attaining very strong glass. Okay. All right. To me, this is the most amazing slide in the entire presentation. To be honest with you, every time I see it, I am shocked. A few years back, not many, I'm going to say 12, 14 years ago, these folks, Professor Delbert Day, Missouri Rolla, and Steve Young, who was at the time his graduate student, came up with a very specific type of glass, also a borate glass, that can be manufactured very similar to fiber or wool fiber, the same stuff using insulation. It looks like this. You can see it. In the United States, sometimes it's nicknamed cotton candy because that's a kind of, you can buy a treat made of sugar that looks very similar to this. But this is made of glass, real glass. And it looks like you see here in the electron microscope image, it looks like a jumble of fibers. Remarkably, what is amazing about this material is that when people have what we call a soft tissue wound in muscle or in other parts of the body, some people have a hard time healing that wound. If you're diabetic, for example, if you get a wound in your feet, the diabetes oftentimes prevents or has harmed the body to such an extent that blood will not flow to the extremities very well. So when you get cut on your foot, there are no red blood cells, white blood cells, or anything else to repair the damage, and therefore you can get infections, you can get damage, other more serious conditions. So whenever somebody with such illnesses gets a wound, it is a very serious matter. It can turn very dangerous very quickly. What these folks invented, this glass wool, can be placed in the wound. You see it right here. Okay, so this is, I apologize if you are sensitive, look away, but these are actual wounds. You can put the glass, I repeat, the glass inside the wound and leave it there. When they first proposed this idea to several doctors, there were 2 doctors who told them it would be immoral to do this. But it turns out that glass does some amazing, amazing things. The first thing it does is that it behaves very similar to gauze. It creates a barrier preventing bacteria or viruses or whatever, or dirt even, from coming into the wound. Second, it provides bridges for tissue, little tissue, because the tissue has a hard time growing because the wound, again, is in a person who doesn't have that ability. But whatever tissue grows will grow into this infrastructure, into this scaffold, and will be able to slowly bridge the wound, which it could not do before. And also, if you use normal gauze, when the nurse changes the bandage, it literally removes any of the growth. This will not happen. The glass is there permanently. Over time, the glass dissolves, just like the nanopart or the microparticles that you saw earlier. As it dissolves, the chemical elements, including the boron, but also calcium and strontium and a few other things, bathe the wound. And it turns out a surprising discovery was that these materials tend to cause angiogenesis, meaning they are nutrients that spur cell growth. So it incentivizes the body to start creating more cells and repairing the wound. And so what you see here is a wound that has been healed to completion for a person that had this wound for over a year without being able to heal on its own. Put the glass wool in within typically anywhere from, I'm going to say 2 months to 5 months. The wound, depending on the depth of the wound and so on, is completely healed. This is now approved in the United States for human beings as well as for animals. It was originally approved first for animals, and now it's approved for medical care in the United States as well. Okay, remarkable product, remarkable invention, 100% glass, 100% borate containing glass. I'll now shift a little bit so that you can make sense of my tour a little bit in a minute. You can also make glass in strange ways in the laboratory. I don't know, Gopi, if they've had a chance to make glass there in your labs, but there are several ways to do it. You can certainly get lucky and take a crucible out of the furnace and have the crucible, the melt in the crucible turn into a glass. But you don't always get that lucky. Frankly, most of the time you will not get that lucky. So there are other tricks. There are many. I'm going to just talk about one. In my lab, we can actually make glass through a process of levitation. And so what we do, and again, let me skip ahead a little bit. We do a specific type of levitation. And in this levitation, let me just go over here. We start with these plates that have these little holes in them, or not holes really, more like wells. And you can put your powder in there, just like you do for normal glass. We then mount it in this setup, you'll see it in a few minutes, and melt it using a high power laser. When you do that, you get little spheres, not microspheres, these are millimeter sized. You can see one sort of up here, okay, and I'll show you a few pictures later, but those are not glass. They are a crystalline sphere, but they are small and they are round and they have been melted. You can crush them and remelt them if you like, but eventually we have a stockpile of several of these spheres. Many advantages. The laser can reach temperatures of 3,000 degrees Celsius, which means you can melt almost anything you want. And you can use different materials, of course, to do this, different chemicals. Once you have the spheres, we change and we insert this nozzle, and we're going to put one sphere in the same place. We're going to put it right here. We then inject a gas from underneath, and that will force this little sphere to float in the air. So the gas comes out and it pushes this little bead, this little tiny sphere up, and it makes it float. So it is not touching anything. We then turn on the laser a second time and melt this bead, this sphere, a second time, but this time we melt it while it's floating in the air. That means that has many advantages. No contamination, because nothing is touching the glass melt. Number two, no problem with temperature, because we can get to very high temperatures without worrying about melting the container, right? Any crucible that you use has a melting point. We use platinum crucibles in our work. Platinum crucibles can only go up to about 1700 degrees C. We have glasses that melt higher than that. So if we tried it, we will melt the crucible before we melt the glass. So here with the laser, we can reach much higher temperatures, don't have to worry about the container, okay? And finally, and most importantly, it turns out that container, that crucible, has a negative effect on the glasses, because as they cool down, the fact that they are in contact with the walls of the crucible can drive crystallization. And therefore, your pretty glass immediately gets crystallized and you no longer have a glass. So by doing it this way, we can avoid, we can inhibit crystallization, surface crystallization in particular, and get glasses in materials that you could not do any other way, like pure alumina. So aluminum oxide can be turned into a glass. And it's beautiful. They look like this. So you have some pictures. You actually see this is the ceramic bead, then you've levitated and you get a very beautiful glass, transparent glass beads. Here are some mixtures, several beads, very homogeneous glasses. You can check them. They're beautiful glass. And again, in some cases, you can get glasses this way that cannot be made any other way. So remember this. I'm going to show it to you in the lab in a moment. And then finally, my last slide. This is actually something that surprises people when we talk about it. There is sort of a fundamental question about glass. Glass, in many ways, it is, from a thermodynamic standpoint, a non-equilibrium material. And so for many years, we have pondered what happens to glass over the long term. Again, billions of years. I'm not talking about glass flow. Glass doesn't flow. Again, we discussed that before. I'm talking about other changes to the glass. And in the latest analysis, which was published only a couple of years ago, the conclusion that we have reached in the glass community at this moment is that glass will eventually disappear. Glass over many billions and trillions of years will go towards crystallization. So all glass will eventually turn back or prefer to turn into a crystal. That is somewhat sad for those of us that study glass, but again, not something any of us are going to be around to witness since it takes so long. But it is kind of curious that glass, therefore, even right now, the windows in your building are slowly, very slowly, an atom is moving here, another atom is moving there, and slowly over unimaginable timescales, they are all going to end up in a crystal arrangement. So I don't know, to me, that's sort of remarkable. And I don't know, just curious that glass is almost a living thing that has a life. It has been created in furnaces, it's been created in volcanoes, it's been created in many places, but it has a life. And eventually it will go back to being a crystal. All right, I think I'm gonna finally be quiet. That took about 10 minutes long, 5 minutes longer than I thought, but I'm happy to either take some questions now, Gopi, or if you want, I can start the tour and answer questions as I walk.
I need to ask students, am I audible? Can you hear my voice?
I'm sorry. I can hear you. Does anybody have a question then?
Yeah, so let me ask the questions from the students, but I also have a couple of questions. But before that, I will
Good.
From anybody question पूछना है तो हिंदी में बता दो, मैं इंग्लिश में बता दूँ.
And they can be about something else too. They don't have to be specific to what we covered.
She's coming. Manu, are you audible to you?
I can hear you. I cannot hear her very well. But if it's a problem, you can also type it in the chat if that's better. Okay, that's better. I should be able to hear you from here.
So my question is, when we convert or we getting glass from the crystals, anything is left behind it, or just changing crystals from the glass into glass?
Are you talking about the death of the glass? What I was talking at the end? Is that what you mean?
Yes, sir. Yes, sir.
Okay, yeah. So yeah, no, I think the entire material would convert to a crystal. There should be no glass left. Now, if you happen to have a glass, you may have learned in school that there can be something called phase separated glass. That's like two types of glass mixed together. Each one of those may die at a different time. So in something like that, you could get crystal, again, over billions of years we're talking about, and then some of the glass may take longer to crystallize, but it will all crystallize eventually.
Okay. Thank you, sir.
Oh, you're welcome. Just in case, to add a little more to that, part of the reason that we like the idea that it crystallizes is because in some of your thermodynamic classes, you may have studied entropy. And one of the problems with glass is that it's disordered permanently. So it would have essentially a value of what we call structural entropy that doesn't disappear even when you cool it down to absolute zero. And that creates something that has been called the Kausman Paradox, which is an interesting idea, but the way we get around that is that glass is not in equilibrium. And these laws of entropy and thermodynamics only apply to equilibrium systems. So we have to, the trade-off is that we have to accept that glass is not in equilibrium, and over time, it ends up being a crystal, and therefore the entropy disappears. Anyway, sorry, a little more detail there. Go ahead, next question.
Mario, we have some more questions, like girls are raising their hands to me, but I also have to discuss certain things with you, right? So it time because I know that.
I have time, but I also don't want to keep the students too long. So what if I keep answering questions while I walk towards the lab? Would that work?
It's perfect. Yeah, please come. Please come.
Hello, sir. So my question is, in the beginning, you discussed that nuclear waste can be converted to glass to prevent
Yes.
it radiating. But the last point was that glass eventually dies. So what if we convert the waste into glass and then it crystallizes back again?
That's a good question. Now, fortunately, the time scales are very different. So for nuclear waste, you are talking hundreds of thousands of years to get the radioactivity once again to decay to the point where it's no longer dangerous. Many of the models are done on the basis of 1,000,000 years. 1,000,000 years is nothing compared to the time scales that I'm talking about for the death of the glass. So the material, the radioactive material will long be extinguished, if you would, before anything happens to the structure of that glass. But it's a valid question. I'm glad I hadn't thought of that. That's a very, very good way to connect the 2 points.
Thank you. I must add to this that we have very intelligent bunch of girls here. So what we are looking forward after this meeting, our principal ma'am will also join, is to extend our collaboration, right? Like I was there and then I got so busy in my job and also there was a gap. Now we wish to cover this gap and have some projects which allow students mobility to your place. So that students can come for 1 month, stay in your campus, do this work, and then can come back.
We do that, as you know, Gopi, with other universities. I have an Italian student that's coming here in about month and a half. We do that in the summers in particular, as you may remember. That's actually the best time for us. But for the record, I'm also happy to, that is a very nice, it's sort of a more high level collaboration. I'm also happy to do more Zoom things because obviously that presents convenient way for students to,
you know, hands-on experiment. So for that, we are planning to bring a group of girls, and then we
yes,
have possibility of fundings together because it's the international year of glass, so we can submit to Fulbright or some other fellowships to fund, and we can write to NSF, and then we have wrote for myself.
I am happy to explore any possibilities, within reason. Obviously, we cannot take 20 students, but we'd be happy to host 1 or 2 of your students.
That's right. Yeah, my students want to be there on the new building, which even I haven't seen. It was renovated when I left.
Okay, keep the questions coming, and then maybe after 1 more, I will start walking to the lab because I do want to show them the laboratory.
Okay, sure. Please, we will start walking towards the lab, and meanwhile, we will take 1 more question. And you So I will ask a question. You can start walking. So
do it. Yeah.
So my concern is about bioactive glasses. So when we have these kind of pattern where we like fill and get this recovered, because it's very interesting field. And my colleague Dr. Neetu has one a little bit late. So she's sitting on my left hand side. I don't know if you can see her.
Gopi, I may need you to come closer to the mic because there are times in which it gets a little slurred, the conversation.
So I think it's much better now.
Yes,
right?
yes, much better. Yeah.
So I'm going to call my colleague, Dr. Neetu. She works with me as a glass scientist. We're establishing a complete glass lab here. So we were talking about, hi, she's
Hello,
Dr. Neetu.
Hello.
So we're talking about establishing the work in the biomedical classes or the bioactive applications. My concern is the protocols, like really doctors allowed to use these kind of products or bandage, and is a patient comfortable? So what kind of protocols you have to use in US, to get these approved? Because in India, I
Well,
know creative.
let me be very blunt with you, very honest here, Gopi. So as you know, I edit a journal, right? The International Journal of Applied Glass Science. I get a lot of articles on bioglass. And the first thing that happens is that almost none of them have a medical component.
Yeah.
And by that, I mean that almost none of them work with doctors or in any kind of real world clinical setting, okay? Most people study only the glass
Yeah.
And they normally do a very simple study in which they show that the glass under the right conditions using what we call simulated body fluid can actually yield and deposit hydroxyapatite.
Yes.
I will tell you right now, I do not publish those papers.
Yes.
Because those papers are anyone can do that work. And it does not mean that just because it forms hydroxyapatite in the lab, that is clinically useful.
Yes, that's what.
You know, and so I think the more, let's call it, that is the lowest level of work. Let's just say that. The next higher level of work is still not to use clinical, but there are multiple other protocols, as you call them, that use things other than simulated body fluid, and that check also for things like cytotoxicity, for example, and things like that. That you can still do in the lab, but it makes the work much more complete.
Okay.
And those papers I would certainly consider for publication, you know, if they have enough novelty and all that.
Okay.
And then finally, the gold standard is to do exactly that, and then include a clinical component where you can show that this has been used in some kind of animal trial or something like that, where you can show that this was a great, you know, it had better than average response to healing bone in animals or whatever, right? So that's that would be the gold standard. So if you can develop a collaboration in your city, for example, with a clinical, maybe a local medical school or something where you have access to animal models, that could be a possibility. That would certainly be more valuable than, frankly, you make a glass, you dip it in a test tube with some simulated body fluid, and then you do some chemical analysis. That's not, to be honest with you, that is no longer, that was great news 25 years ago. That is no longer the standard for good level research.
Things have changed since a lot Hench has worked on it.
Yes, exactly.
Okay, we can start working.
Okay, perfect. Okay, can you guys still see me okay, I hope?
Yes.
Perfect. Okay, so here, let's go one step at a time. Now I'm in my lab. So you can actually see here, let me see if I can set it down so it's a little more stable. Maybe actually, I don't know. So if you look here, oops, let me go back, let me exit the talk, there we go, better. So here you can see this is the setup of the aero levitation that I was talking about. So this is the famous sort of, this is just a protective shield right here that is just to prevent, of course, the laser, scatter light from the laser from going anywhere near your eyes. These are this is a couple, I don't know if you see them here, of those plates we talked about for the chemicals to go into. And then those plates go in here, inside there, where you actually then have the laser coming down from the top. As you can see, everything is shielded by this plastic tubing, again, for safety. And then you melt the glass first. You then replace it with, of course, our friend here, the little nozzle, okay? And then your bead will levitate from here. Again, you melt it a second time. What I didn't say last time is that we do other things. We don't just melt it. Over here, if you look, you'll notice that we have a camera right here. Okay, this is one of those fancy cameras that can do 40,000 frames per second. We can film the bead while it's levitating. Remember, when it's levitating and when the laser is on, what you have, it's a liquid. You have a liquid, a drop, liquid drop that's floating in the air. We can then, if you can believe this, put speakers. So sound speakers. Okay, sound speakers in the chamber. Okay, and then we can put sound in the chamber and force this liquid drop to start resonating with the sound waves. And we film that. And what we can then do is when we achieve resonance, when we can get the drop to when we find the resonant frequency, to be exact, of the drop, we can calculate from that the surface tension. And then we turn the sound off and we wait and see how long it takes for these oscillations to die out. And from the time it takes to die out, we can get the viscosity of the liquid. So think about it. This is a liquid at 2000 degrees Celsius, and we can measure viscosity. We can measure surface tension, even though it is an incredibly hot material, and we can still get that from images, from the film, essentially, that we get that, okay? And analyzing, again, the changes in the position and things like that. So pretty cool setup, very nice. The disadvantage, of course, is that it makes very small amounts of glass. It makes tiny little beads. On the other hand, if you are interested, there are ways around that problem. You can grab many spheres and sinter them together into a lens, for example. I have a colleague who's done some of that at another university. And then the Japanese have developed a method called in-flight melting, which is not levitation, but you drop the material and melt it while it's falling, which creates the same conditions, right? No contact, high temperature, etc. So people have actually done similar stuff without using laser melting. Okay, let me keep going here. There is another instrument over here, if you see it. This instrument is very different. I'm sorry that it's not so visible. Maybe I can do this. Let's see. Yep, in there. So what you see here, let me hold it this way. So this dark thing, it's a laser. And this over here, this tube, this very shiny tube, is what we call a time-of-flight mass spectrometer. So what we do in this particular setup is that we mount a sample on the back end over here. Let's see it. There we go. There we go. So in this hole, we insert a sample that goes into this chamber, which is in a vacuum. And then while it's there, let's see if I can show you this better. While it's inside the chamber, we can turn on the laser and pulse some high power, well, low energy pulses of light, hit the sample and remove atoms and molecules. Then what we can do is wait for a few microseconds while those here, so I don't have to, there we go. So they are removed down here and they fly. Once you remove them with the laser, they fly down this tube. They get turned around down here, they fly down and they hit a detector right here. And it turns out that with some calibration, you can actually calculate the mass of each atom and each molecule from the time it takes to arrive at the detector. So you can destroy the glass in a way, but we do it so gently that we can get relatively large molecules. So not 1 or 2 or 3 atoms. Those are not that interesting to us. If I make a silicate glass, I know that I have SiO4 tetrahedrons in the glass. I don't need a lot of instrumentation to tell me that. But I don't know how they are arranged. Do they make rings? Do they make chains? Do they make other things? So this allows me to see larger molecules, 10, 15 atoms, which in turn I can study to see if I can understand the what we call the intermediate range structure of the glass. And so that is the use of this particular instrument. So it's used primarily for basic science, although, Gopi, you were talking about biomaterials. This same technology, as you might know, is used for something called proteomics, which is the study of protein structure using the same exact method. And so it's kind of interesting if it's for biophysics is strong overlap with this instrument. Okay, let's see what else. Let me show you something simple and then there's something more complicated. This setup over here, very simple setup. It is designed to measure the contact angle, okay? So we put a drop, we put a glass over here on this platform, then we put a drop of water, very, very high purity water on it. And then we have over here a source of light and a camera that images how the wetting behavior, how the shape of the drop of water on the surface. When you have what we call a wetting material, the drop will spread out. when you have a hydrophobic material, the drop will tend to group itself up and make more of a sphere. And we can calculate that angle, the wetting angle, from this. And what we've been doing over the last, I don't know, a couple of years is working on developing glasses that are what we call super hydrophobic, meaning they repel water exceedingly well. And so, as you know, Gopi, we make many, many glasses. And so we have studied many families this way. The surface has to be very clean. And so over here, you see there is another piece of equipment. It's an ozone cleaner. So it bombards the surface of the glass with ozone to clean it. We also do other steps. So that's a simple measurement. It's not that complicated to calculate the angle, for example, but kind of interesting. This one is, on the other hand, a much bigger, as you can see, much bigger instrument. There we go. Like this and like this. So I want to show you there are two parts to it. This white box right here, and then there is, let me see if I tilt, am I tilting the wrong way? No, here we go. And then we have this other instrument right over here, this guy over here. So they are very different. This white one over here is a Raman spectrometer. You may have one at your university perhaps, or maybe at a close university. It is a pretty standard tool for doing spectroscopy. It is what we call a Raman. So it has a microscope essentially that uses where we can mount the sample on the microscope and take a picture visually, but also deliver the laser light. I can do this in a way that you can see it. So these same lenses over here are used to visualize the sample, but also to deliver the laser light through these lenses. And so we can choose the magnification and also simultaneously the size of the laser spot that comes out at the same time. That in itself is very cool. We have two Raman spectrometers. We have another one in a different room. But this other tool makes this even more remarkable. This is what we call atomic force microscope or scanning probe microscope. So as you may know, they use a little needle, if you like, or a microscopic needle to analyze the surface, to determine the topography of the surface, bumps, valleys, ridges, cracks, any kind of surface feature can be visualized by this needle tracing the features on the surface. What makes this instrument very unique is that right over here on this Raman spectrometer, there is a hole. The laser can come out of that hole and into, I don't know if you can see it, but into this hole, which it means that you can actually have the laser light go into the microscope, the atomic force microscope. So you can simultaneously map out the features of the surface while the Raman laser analyzes the chemical, technically the vibrational spectrum of the material in the same spot. So you get two types of information. If you have a mountain, for example, a bump, you know there is a bump, and the laser will tell you what is the the vibrational signature of that bump. So that's pretty cool. And that's a pretty nice tool to analyze. We didn't have that when you were here, right, Gopi?
No, Raman wasn't here. Raman is a new addition. I think you purchased
Yeah,
it
that
and left.
I think a few things here are new additions. I'm trying to show you too some of the new stuff. We have other stuff around here. That is another, that too. I'll get closer so you can see it. Here it's another.
But there was a melt quenching setup also, right? In which we have a furnaces and then there were the rollers for the crushing.
Yes. Yeah, but remember that since you were here, unless I'm mistaken, we renovated the building as well. So it might not be recognizable to you, since then. Here is another atomic force microscope. This one is older, but I really like it because, as you can see, it's much more open. So it's easier to teach the students how it works so that they can see, the details and the inner workings of that. So this is, I'm skipping a couple of things, but this is just my lab. So I'll just quickly walk over, and then again, we can take some questions as well, Gopi, if you want at the end again.
I must tell my students that he joined this institution as a student. No, he's in a chair in head of department and so you can see.
Give me 1 second. I know it's like kind of dark in here, but that's just because the light turned on yet.
So
There we go.
see that as a student also, I will show you his pictures. He's sitting on the floor, reading books here in the same building, and that he has constructed the devotion for his own institution, where he worked, he studied, and he took doctorate from outside, right? You did PhD from Iowa, I think.
PhD from Iowa. Who got that?
I said that you have studied from core, right? You were alumni.
Yes.
Yes, and I want to tell these students, okay. I want to tell my students that you are alumni, and as alumni, you have worked so much, and now you are heading this like core stuff, and you are holding like, your chair. For them, chair is head of department.
There is something very nice about being able to help or to help improve the school that you went to. There is
Yes.
something, I don't know.
The community where you can work and where you could grow, right? Because you know the roots and everything. So like we guys are old. I am also old. So it is their generation now. Either they take our setup further or they can do whatever they want to do.
You know, when I was a student at Co, I remember listening to an old president of the college. He was no longer president, but I remember he said something in a speech. He gave a speech to a student group, and he said that it is a noble life to work at a university and to be able to actually help, you know, do the kind of things that professors do at universities. So I don't know, that always stuck with me a little bit. Let me also show you a couple of things there. I'm sorry about the quick spinning. This is an X-ray diffractometer. So standard, this is nothing special. You know, you put a crystal in here, you can analyze the structure. You can put a piece of glass in there and check whether it contains any crystals in it. On purpose, if you made a glass ceramic, or not on purpose, if you are making a novel glass and maybe without you knowing it, a little bit of crystal snuck in there. So we can test that in here. A few years ago, we did a very long project, very good project on the electrical conductivity in glasses. So most glasses, as the students I'm sure know, are insulators. They're great insulators. But there are certain glasses that conduct electricity fairly well. Let me see if I have in here. Oh, good grief. Here we go. So here is one example. Okay. Fairly big glass, as you can see. This glass conducts electricity. It is not as good as a metal, for example, of course. But I can tell you that we can make this glass, different composition, so conducting that you can measure it with a multimeter in the laboratory. So it is almost the same as a standard low resistance, you know, a few ohm resistor. So that would be very high conductivity glass. And we were developing it for detectors to be specific at CERN in Switzerland. And so those detectors were prototyped and they work. I think our latest model was 1,200 times faster than the current detectors that they have, which is what they wanted. They wanted something that would work faster. So by making the glass more conducting, we're able to process the signal more quickly and therefore accelerate the, what they call the duty cycle, how often you can make a measurement. And so that is what the glass was for, and it worked. So that was a good piece of work. Again, new things we have here. Here is a nice harness tester. So whoops, let me see, here we go, yep. So with this guy, you can use the diamond. It's a Vickers diamond, so you can poke into a material and see how hard the material is. So this is for the study of mechanical properties. Then over here, again, new is we have another professor, a new professor, and he studies ionic conductivity. So this setup over here can measure
But now, आउटपुट तो कोई भी चलाओ, इंटरनेट पे लेना, हैं? चल रहे हैं? अगर आप लोगों को इंटरेस्ट नहीं है तो मैं टॉक खत्म कर देती हूँ, क्योंकि हमने बात करनी है इसके बाद बच्चों को वहाँ लेके जाने के लिए, उनको यहाँ बुलाने के लिए। मतलब फिजिक्स डिपार्टमेंट में जो रिसर्च कर रहा है उसका जो मेन फील्ड है वो ग्लासेस के ऊपर रिसर्च है, और इट्स सो वन ऑफ द बेस्ट इन
Ah, there we are.
recognize games across words.
Okay.
Sorry, there was a break. Power failure.
Oh, no problem. Can you hear me okay still?
Yes. Sorry, there was a power failure on our side.
No problem, no problem. But you gave me a chance to come back to the office so I can answer any more questions the students might have.
Yeah.
I think, I mean, we can keep going for another half hour. You know, we have the furnace room, the DSC room, but I think for the nice equipment, that's probably a good summary of the nicer equipment.
Yeah. Actually, meanwhile, I was talking to my students because see, at this point of time, because we have a KMB, let me tell you, like we have muffle furnaces, we have purchased a glass furnace, we have muffle furnaces, we are still following the melt quenching technique. We haven't done the laser part yet for the preparation part, but we are using melt quenching. And for the characterization, we have UV, we have FTIR, we have PL from Perkinelmer, and we have DTA from Nestec.
Good.
Yeah, so but we don't have SEM or TEM or XRD, so we are lacking in that, and for that we send the samples to nearby places to get the data and so on. So the first point for which I'm looking, as I said, that we will discuss about possibilities of collaboration is number one, that we can prepare combined compositions. So we can decide. So for example, we have prepared the samples here. We can send it to you for XRD, for Raman, and the hardness measurements. You have Wicker hardness and the conductivity, but compositions we will decide. Composition.
Yeah, well, remember that it's not just compositions, the size of the sample will be different.
Yes, to be fitted and all that. So these preliminary discussions we can have. And then I can take one student from this side who will do the PhD in the same. The student will get a doctorate degree, and the KMV will give the money to the student.
Good.
Yeah. So we are actually our president joined here your talk for a moment, and then she sneaked away. She just she joined, but and then she has left because we have not many things tonight. We have already spoken with her, and we have advertised the post. So we are planning to have 2 students from KMV side. What's his connection? Hi, sorry. There's some.
I don't know. It might be our fault too. I mean, it doesn't have to be you guys. Sometimes we have internet issues too.
We have already advertised the post in newspaper so that we are calling for applications. Students can apply. So the KMV will provide a small amount of money as a salary to work into the seed money project. We call it as a seed money for research. So they have given us seed money to nourish the research. So we will prepare the samples here. So option number 1, that samples will be posted to you for second set of characterization. Of course, compositions will be decided in the beginning, and then combined publications can be made for the work, number 2. And then the student will submit the PhD thesis, taking you as a PhD co-supervisor.
Like I did last time for that other thing.
No, that was a reviewer. You were reviewer.
Okay, gotcha.
As a supervisor, not as a reviewer. Then we have to find out another set of reviewer. So that is a one option. But during for that, I will prefer if student can actually come there also.
Yeah.
For that we need to submit project for funding, like travel, visa, everything and all that.
Well, like I told you earlier, Gopi, I'll be delighted. I know your students are probably be very excited to come and visit the lab and spend time here.
Yes.
I think we just have to work through the details, honestly, times, dates,
time,
visits,
dates,
projects, classes.
Yes, truly, truly. So for that, I will create a group of a few of us in which there will be students and there will be teachers.
Okay.
Okay. So we'll be start
Sure.
communicating mails. So the call for proposals from your side, like NSF or so, I will formulate the project, or from our side, Fulbright or anything which comes on the way, which can support.
Yeah, we have to talk about it. You know, NSF is a bit tricky with these international grants. They used to be easy. Many years ago, you could apply for an international grant alone. Now it's getting complicated. If you have, normally they want you to put it in your actual research grant, not as a separate grant. So we can talk about it, but there might be other sources of funding as well.
So that's a plan, because we have got the seed money from our side, and the
Good.
two grants which we have, we're getting from college side. One we will attach with you, and another one we will attach in my Italian groups.
Yep, I remember.
Yeah, so then at the one point of time, we three can collaborate together. So first of
Well,
all,
let's start with something concrete. So let's have a, like you said, create a group, and we
Yes.
can start discussing something
Create group.
concrete that we
Yes,
can look at.
peer group, exactly. First of all, we'll branch it out, and then at the later stages, we can uniformly, you know, make it a global research or a global village kind of thing.
We can look, yeah.
Yes.
But let me ask, do the students have any other questions about glass at all, or?
So, yeah, house is open for students. And please, raise your hand.
And it doesn't have to be about the talk, guys. If you have any questions about glass, I'm not sure I know all the answers, but happy to at least take the question in the first place.
My question is, what is the need for electrically conducting glasses?
Okay, so maybe Gopi, can you repeat, get closer and repeat the question?
Is asking what is the need for electrically conducting glasses? What is the requirement?
Ah, yes, good question. So to be honest with you, there is a few ways to get electrically conducting glasses, but the truth is that even if you go around and around, vanadium is what you need. That's the gist of it. Vanadium in the glass, to be exact, vanadium pentoxide, V2O5, can create two different sites in the glass, two different states of the vanadium, V4, V5 plus, V4 plus, V5 plus, and that allows for the electron to jump from one vanadium to the other. And as long as you have a reasonable amount of vanadium in the glass, these locations, these sites, allow for what we call hopping conductivity of the electrons. And so the electrons can actually flow pretty easily in a vanadium containing glass. It's not the only way. You can have iron in them sometimes and make the glass pretty conducting. You can also add phosphates, but in general, to be honest with you, the winner is vanadium by a long shot.
Okay, one of the question is passed to me that can we guess glass with the naked eye? Is a glass or crystal? If we have a glass, we have a crystal. Can we tell?
Yeah, normally, yes. The glass will appear very transparent, of course, whereas a glass that has some crystal will appear more opaque. And it's a glass, it's sometimes hard to tell whether it's crystal or phase separation, but it looks like a milk or a milky appearance, almost like a drop of white paint in water. You get a little bit of that cloudy appearance to the glass. However, one has to be careful because, for example, the glass I showed you earlier, the vanadium glass you were asking about, is pitch black. It's absolutely dark. So it's very difficult to tell. You cannot look through it. So you can't tell if there is any crystal in there. So that's a little more tricky. That would require XRD measurements to check. The other thing I would say is that even then you gotta be careful because in some rare cases, you can have very tiny crystals. nanometer, meaning about say 30, 40 nanometer crystals. Those are so small that even in a transparent glass, you might not be able to see this kind of crystalline presence in such small clusters. And so there, once again, you need to perform more, more adequate measurements like an XRD. Even then, even with the XRD, you have to be a bit careful about the way you measure. But either way, yes, there is 90% of the time, 95% of the time, you will spot crystals with your eyes. But there is that 5% or so that sometimes can be a little tricky.
One of the project which also comes to my mind once we started discussing with Italians is the heritage glass, the glasses which are imparted in the building, palaces, cathedrals, many years of this. So when they get renovated, if it is possible to procure some small amount of those glasses and study their optical properties, that it can be really
Yes.
very interesting.
Yeah, our journal gets less frequently, but about once a month, I get an article on archaeological glass.
Archaeological.
And yep, archaeological glass, typically analysis of where it was made, or like you said, Gopi, some interesting optical properties, some of the work by alchemists that were making nanoparticle containing glass. Yeah, it's a very interesting topic. And sometimes the science, the glass science behind it is also very interesting.
Yes, because in one of my projects, I gave reference of surface plasmon resonance, SPR, surface plasmon resonance on the cathedral glasses. And the
This is for nanometallic particles.
Nanometallic particles. Yeah, exactly what we were talking, that nanomaterials are here, metallic.
Yep.
But
Yep.
which changes the color.
Oh, absolutely. And as you know, the size matters a lot for nanoplasmon resonance. So yeah, those are, I mean, it's amazing to think that people were making those things. They didn't know what they were doing, but they were making such things.
Yes.
Incredible.
Yeah, I think students have another class to catch up. So we can, and I think it's a midnight for you, right? It's midnight.
It is midnight. It's about 7 minutes till midnight.
7 minutes to midnight. Oh God. Girls, don't you deserve a big round of applause so that we can...
Thank you. I am delighted. Thank you again for coming. Enjoy the rest of your day. I know for you it is just beginning, but yeah, Gopi, you and I should definitely set up. That group is fine, but also set up a separate chat, maybe with some of your colleagues,
Yes.
a Zoom chat at another time
I will make
to
first
talk.
Start exchange emails, then decide the timeline, projects, students, and everything. Okay.
Yep.
Yeah. Take care.
Sounds
Bye.
good. All right, guys, thank you very much. And I hope, I wish all the students well with all of their studies, their work, their thesis, everything else.
Thank you. Ciao, Unubachi.
Ciao, bye-bye.
Ciao. Bye. Okay. थोड़ा जब क्या करूँ क्यों टेस्टिंग करते हो बिल्कुल मुंह में नहीं जम जाता है totally nobody asks any